Now, it's something that we've talked about at a fairly high level, occasionally at a fairly low level, to support some of the other conversations we've had about processors and the structure of the system and how the memory connects to everything else and all that sort of stuff. Generally, the whole idea of computers having memory is working space, okay? It's space to hold the applications that it's executing. It's space to hold the data that it's working on at that point of time. And the reason why we use memory for that rather than mass storage is because memory is a lot faster. Still nowhere near as fast as the processor itself these days, but at least it's a pool of fast enough memory so that the processor's not waiting forever trying to get information. There's a few techniques and so on about making, from memory getting the data to the processor in a fast enough way so that the processors can actually get some semblance of efficiency going on in terms of making sure that it's keeping those pipelines full of instructions and pushing data out. Okay, so as we've sort of alluded to before, modern processors run several times faster than the memory that's attached to it. Okay, and there are two performance metrics really that govern memory, and first of all there's the transfer rate, which we'll be talking about today, and then there's the latency that we'll be talking about on Thursday. Just to start things out, okay, we've been talking about processor cache a few times. When I was talking about processors, I was saying that the higher end processors tend to have more processor cache. Now, at that time you were thinking, I'm not really sure what processor cache is. What it is basically it's some really, really fast memory that actually is either at or very close to, the interpretation of very close to in these sorts of system designs is that it may run half the speed of the processor or something like that, but it's generally memory that can keep up really with the processor. Now, the reason why all the memory is not the same speed of cache memory is because cache memory is incredibly expensive. It's kind of like that thing of, if the black box flight recorder in the airplane survives a crash, why don't they make the whole plane out of that material? Okay, and there are just fundamental reasons why. Obviously with the plane it'll be way too heavy to actually take off. In the computing terms, when it's talking about memory and cache, it's because cache memory is so expensive you'll end up spending, $50,000 to buy a computer. Okay, the type of memory that cache memory is made up of is fundamentally different from the memory that you get in modules to use as general memory. Cache memory is what's called static memory. Okay, and that's generally, it's a lot more electrically simpler to work with. Okay, the memory is there as you would expect it to be, and you ask it to do something, it'll do it. It doesn't need to refresh itself and all these sorts of things. And as part of all that, and also it's also a lot faster, but as part of all that, that's what makes it really expensive. The typical sorts of memory that you get on computers is dynamic memory. Okay, and that's memory that has to constantly refresh itself, and being able to access it is a little bit more difficult than with static memory. And you'll hear something about cache SRAM, SRAM, static random access memory, and DRAM, dynamic random access memory. Now the type of memory that is in most memory modules these days is called SDRAM. In that case, the S doesn't stand for static. It's not static dynamic random access memory, because that just doesn't make any sense. The S in that case refers to synchronous. Okay, and that's all to do with the timings of how the memory actually interacts with whatever it's connected to. All right, so the idea about cache is that if you've got a processor, we sort of took it to be similar to an assembly line, and that is that the processor can only work as fast as its slowest component. Okay? The weakest link in the chain determines the output of the entire system. So if we have a fast processor coupled with slow memory, it's the memory that's going to limit how much data and instructions can get into the processor, and that's going to affect how much output is going to come from the processor. Okay? So the idea of cache memory is to sort of speed things up a little bit by having a small pool of fast memory and using some special tricks and so on and so forth to try and make sure that that really fast cache memory has the information the processor needs when it's going to start accessing, or when it's going to start asking for it. Okay, so we were talking last week about how processor pipelines have some speculative algorithms to guess what branch is going to be executed next, or guess what section of code is going to be executed next. Same sort of thing happens in the memory controller, or the cache controller, to sort of say, you know, I'm accessing a lot of this memory like, you know, just linearly. What I'll try and do is that whenever I have a spare time, I'll actually dump the next set of memory in that sequence into the cache. So that means that by the time the processor asks for that, it's already there. That's a very simple kind of thing that it does. Again, cache algorithms are just as complicated as the branch prediction and so on that's used in the processors. So that's a topic that's well outside the scope for first year computer science. Probably maybe, you know, it's probably, you know, more of a final year or a digital systems engineering sort of thing. But there are those algorithms and so on, and you may end up seeing some of those in other forms, and that's because the idea of cache actually is translated very well across many parts of the computer, and we'll be talking about that on Thursday. So we've got this ultra-fast pool of memory, okay? It's got these predictive and speculative algorithms to try and get, you know, the data in the right place at the right time, so the processor doesn't have to constantly wait for the main memory. Okay, when a cache actually has memory or actually has data that the processor's wanted, it's called a cache hit. Okay, and the effectiveness of a cache algorithm is basically what's the hit rate? You know, what percent of the time does the cache actually have useful data that the processor needs, so that the processor doesn't wait to have the memory controller fetch it from the main memory. Okay, so modern cache control systems, the hit rates can be exceeding 90%. Okay, now that's actually quite surprising when you consider how small the pool of cache memory is compared to the amount that's in the final memory, and we'll go through that in a couple of minutes. But as always, when you start to look at things in a little bit more detail, things get a little bit more complicated as well. And the fact that computer processors now are so much faster than the memory, a single store of cache is not really enough. Okay. Back when computers were, you know, the processor might have been running at 25 megahertz or, you know, 33 megahertz or something. You know, you had memory that was on the bus at 8 megahertz. It's only a few times faster. So you only needed one pool of cache memory that was, you know, a little bit more expensive. There wasn't any problems in terms of signaling at those really fast rates, or the physical distance between the memory and the processor. And, you know, you could get away with just having one blob of cache that could be worked with. Nowadays, since processors aren't in the megahertz range, they're getting to several gigahertz, there are multiple levels of cache. Okay, and does anyone here know how ship lock works? Like if you have to get a ship uphill, and they've got these series of pools, and every pool fills up with water and it lifts the ship just a little bit more until it gets over this hill, and then it can sail back down, or the locks take it back down the other end. And that's because you can't just lift the ship 100 metres or 50 metres or however high this lock system is in one go. You have to do it progressively because, you know, the engineering's just not there and it's just unfeasible. Same sort of thing here with this cache memory. You have multiple levels. So you have the first level of cache is a few times faster than standard memory, but it's still a lot slower than the computer or the processor. And then you've got intermediate levels of cache from that are smaller pools that are, you know, a few times faster than that and a few times faster than that. And they sort of work together in terms of making sure that the data goes through these caches in such a way that the data the processor needs ideally is in the fastest level of cache. If not, it can go to the next level. Okay, small performance penalty, yes, but it's still nowhere near as bad as being having to get to your data from main memory. Okay, so the first level, the fastest level of cache, is called level 1 cache. Okay, that's the smallest and fastest set of cache memory, and it's typically on the processor itself. Okay, and that basically runs at the same speed of the processor, if not half speed. Okay, and because it is as fast as the processor, there's no delays. Okay, you know, processor needs it, it can get it right away. It doesn't have to wait around or anything like that. Okay, level 2 cache. Okay, that's memory that is clocked slower, okay, because it's cheaper to manufacture. It's easier to organise because if you've got this massive level 1 cache, it's running really, really quickly. So level 2 cache, it's a bit cheaper, it's a bit slower, but they can make a lot more of it. Okay? So that sort of supports the level 1 cache. Okay? If the level 1 cache doesn't have what the processor needs, it then goes to the level 2 cache. Same thing with level 3. Okay? It's a bit repetitive here. Okay? So most modern systems do have all 3 levels of cache, and typically they're all on the processor now. Okay? In the past, it was a matter of you had the level 1 cache, you know, really, really close to the processing units of the CPU, and the level 2 cache, it could have been on the processor die, or it could have been right next to the processor or something like that, but it could very well be in the same socket. If you look at an Intel Pentium Pro processor, this is from about the mid-90s or so, the chip's actually really, really big. And it's got this little gold cover over it, and you the gold cover off of it, and there's actually 2 pieces of silicon on this package. Okay, sort of like the packages that we were talking about with the sockets, those square things, had 2 separate two separate sets of silicon in there. One of them was the processor in the level 1 cache, and the other one was the level 2 cache. Okay, and that was because they wanted it to be as close to as possible to the processor. Now those Pentium Pro CPUs were incredibly expensive at the time, okay, because having to deal with one big piece of silicon is annoying and expensive. Having to deal with 2 pieces of silicon and making sure they both actually work by the time you actually package it into a chip to ship and sell and make a computer out of, it ended up being that was actually a very, very expensive way to produce these processors where you had the processor and the level 2 cache closer in, okay? Because as I was saying before then the computers were only working, you know, 33 megahertz thing. They could just have the next stage of cache on the motherboard, just in memory sockets or in that little cache on a stick thing. What they did to make things cheaper to manufacture is that they put the processor not just on a pin out like a chip with pins, they put it on a circuit board of its own. Okay, it was called the slot type of CPU. Okay, so that slot CPU had a small circuit board, it had the processor and the level 2 cache around it. Okay, and then obviously as they were able to improve their processors in terms of making the transistors on the silicon and miniaturize things a bit more, they eventually went back to putting it onto a single chip package. Okay, so yeah, level 3 caches. Now, historically, level 3 caches were something that were only really on workstation and server machines, and that's because memory is usually quite an expensive part of the computational core of the, and at the kinds of workloads that computers were doing back in the days and so on, there wasn't really that much justification for having level 3 cache. The 2 levels of cache were fine. Nowadays, transistors are so small, and it's a transistors are so small, relatively cheap to put additional transistors onto a processor die. It's a good, relatively easy way of improving performance. So they figure, why not? Let's just, you know, put a few meg of level 3 cache right on the processor itself. And if you do look up processor specifications, say on the Intel or the AMD website, you'll see, you know, how much level 1, level 2 and level 3 cache are on their various models. So you'll have processors that have the same clock speed, same features in terms of all that fancy stuff we were talking about last week, but the level of cache is different, okay? And that can also be that processors, they might, when they build these in the fabrication areas, they'll try and build the best one with the full set of cache and all that sort of thing. But if they find that they were able to build one and the processor works all right, but there's in one part of the cache the memory's not really working right, what they'll do is that they'll disable half the cache, okay, because it wasn't working reliably, so they actually disable that half, but the other half still works. And then they'll sell that as a lower end version of the chip, and this is what's called chip binning. Okay, and this is how you might be thinking, you know, do they actually, you know, there's like 15, 20 models of each model, of each type of CPU. Do they actually make all 15 or 20 as bespoke units? You know, I'm actually making a 3.2 gigahertz processor now, and then in 15 minutes time we'll get the thing to run some 2.8 gigahertz process and all that. That's not actually how it works. What they do is that they try to make everything the fastest, and then through quality assurance along the assembly line, they work out what things don't work properly and what things aren't, what things can't be ramped up to a high enough speed and all those sorts of things. And they sort of have a quality binning in terms of, okay, this process is fully featured, but it doesn't run quite as fast as what we would like it to, so it goes into this quality bin. This one here is perfect, it goes into the top quality bin. This one here is a bit of a Friday afternoon job, it doesn't run particularly fast, and there's some problems with some parts of its cache memory. We put in the low quality bin. And those bins will be associated to various model numbers. And as the process improves, they can sometimes find themselves in a situation where everything is top quality, and they will actually artificially say, we know this is a top quality component, but we'll sell it as a lower quality one because we're not making enough lower quality ones to satisfy demand. And that actually happened. The biggest example of this was Intel when they were making the 486 processor. When they first made it, it was a real big challenge for them to be able to make these reliably. So at that time, the 486 had two versions, one that had the maths coprocessor inbuilt and one of them that didn't. And the way they bin them is, well, does the math coprocessor work properly or not? If it doesn't work, we sell it as what's called a 486SX CPU. And the ones that do work, we'll call it a 486DX CPU. And we sell it for a lot more and we make heaps more money. They ended up making these things so well that they were taking perfectly good 486DX chips and marking them as 486SX and just disabling a perfectly good math coprocessor so they could sell it. But you could upgrade your 486SX with what's called a 487 processor, and that was the math coprocessor to go alongside it. And what the 487 processor was a perfectly good 486DX processor with everything else the math coprocessor disabled. Okay, so they were able to make these things, as they were improving their process, they were able to make these things so reliably that they ended up, in order to satisfy all the market segments, they ended up making heaps and heaps of these really, really good quality things and intentionally breaking them so that they could satisfy particular market needs. Of course, you know, if you were actually an engineer looking at this, you'd say, why don't we just give everyone these 486DX parts? Then there's not a problem because then we don't have to worry about these two different segments and selling them separate coprocessors and so on. But then, you know, the business people gone in, but we do want to sell them coprocessors and we do want to sell them things cheaper. So it was made a good business decision to do that, even though from an engineering point of view it made no sense at all. There was a video I put up on the online notes in week 4. There's a talk, it goes for about an hour and a half or 2 hours or something, of one of the chief architects. That's actually a really, really good video if you happen to have an hour and a half spare and you really wanted to learn more about the real world of processor manufacturing. There are a few good anecdotes there about those sorts of things going on. So that's cache memory. And how it's built nowadays, it's on the processor and all that sort of thing. Okay, so let's talk about the main memory, okay? Because the cache memory is the fast stuff that's expensive right next to the processor, but at the end of the day, we need a heck of a lot more memory than we have cache memory, so we have main memory, okay? It's quite a bit slower, but we can make lots of it. You know, you can buy, I don't know, is it 4 gig of memory for like $20 or something down at the shop, whereas if you wanted to buy 4 gig of static memory, you'd be paying a lot more than that. So if we look at the proportion of main memory to the various levels of cache, you can see that those cache prediction algorithms do a pretty good job of to work out what sort of data to have in the caches at the right time. Because say for a typical modern system, you might have 8 gig of memory. The level 3 cache of a mid-end processor these days will be about 8 meg. Okay, and that's 0.1% of the main memory is the level 3 cache. All right, so if you think about all the stuff that you have in memory, the biggest cache can only store 0.1% of the data that the main memory is holding. And then the next levels go even smaller than that. Okay, and I've messed up my decimal points there. Because level 2 cache, that is not 0.364, it's probably supposed to be something like 0.0364. Okay, and you can see that things get ridiculously tiny when it gets to the level 1 cache. Alright, so I was talking before that there was bandwidth and latency, and these are the two main benchmarks that there are in memory speeds for a computer, because they're two different things. Okay, when the processor requests something of memory, there is how long it takes for the memory to get its act together and actually start spitting out data that the processor's is asking. That's called the latency of the memory, and it's a little bit more complicated than just saying, just hang on a couple of nanoseconds, I'm almost finished here, all right, here you go, here's some stuff to start working on. Because of the way the memory is internally organised, memory latency is affected by a few different things, and we're going through that on Thursday. If anyone here has played with RAM timings in your computer, okay, probably the people that sort of play around with computers as a hobby perhaps have done that. They're the kinds of things that affect memory latency. Okay, and then there's also memory bandwidth. What memory bandwidth is just how fast is the bus to get data to go from the processor to the memory. So you could have a very, very fast data bus, but heaps and heaps of latency, and that will affect the overall speed of the system. At the same time, you might have a memory system that has very good latency, but there's low bandwidth, and in that case it's like trying to drive into the city in peak hour. There's just so much data trying to get through this relatively small data bus that there's a lot of congestion.